Okay, is exam 4 physics 201 actually for fall 2016. Consider this object. It's a square flat piece of metal and each dot shows an axis of rotation. Rotates about an axis that's in the plane of the page. So it's like as if it was rotating about this, it would rotate about in the plane, like the paper would rotate around. Which of these describes the moments of inertia? Well, which object has the highest moment of inertia? Well, about axis A is going to have the highest moment of inertia because I have more mass at big radii. I have a lot more mass at big radii. So A has the biggest, so I can get rid of these. And then I ask myself, which has the smallest? Well, C has the smallest because it has the smallest radii, the mass at smallest radii, but notice C is listed here. And then I recognize that B and D, because of the symmetry, that those are exactly the same. So A is the right answer. Speedometer on my bike measures the angular speed and converts it to a linear speed. It does that based on this relationship. So the speedometer measures omega, and then I put in the radius of the wheel, and it calculates a speed, and that's what it reports on the speedometer. That's how your car speedometer works too. Suppose that I input a radius that is smaller than the actual radius. So what if I put in a radius that is actually smaller? Then it's going to report a speed that is lower than the true linear speed. So it thinks r is small, so it's going to it's going to report a speed that is smaller. But instead my wheels are bigger, so they're actually traveling faster than what it reads. Consider this fan, it's spinning and it's slowing down. So omega, which is the angular speed, is counterclockwise, so it's positive. Or excuse me, no, that's clockwise. Isn't that right? That clockwise? Yeah, so it's negative because it's clockwise, and it's slowing down. That means that alpha is opposite omega, so it's positive. So omega is negative. This gets rid of these. Alpha is positive, so the answer is C. When will an object continue spinning at the same angular velocity? It will do so when the net torque is 0. When the net torque is non-zero, it spins with an increasing angular velocity because alpha is the angular acceleration is non-zero. When the angular acceleration is either positive or negative, it's going to change its speed. And when the net force on the object is 0, well, maybe, but maybe not too. That doesn't really tell us anything about how the object is rotating because I can have an object with net force equal to 0, say this object, rotating about this axis, the net force on that object is 0, but it's going to spin in a counterclockwise direction. You go over the crest of a hill in a car at a high speed and come off your seat. So you're traveling over the hill like this. There's your car. And when you're in it, you sort of come up out of your seat a little bit. Which of these best explain the physical cause for this? Okay, so you got to sort of pick out the best explanation. The normal force is less. Well, you know, that is true, that the normal force, that's the force that the seat is pushing on you, that is less, but that's not the cause. That's just, you know, describing what happens. The normal force is less. Your weight does not provide a large enough centripetal force to keep you in the seat. All right, now that's getting more to the cause. The centripetal force has decreased. No, the centripetal force is still the same. Your weight acts as a centripetal force. It's just not enough. Has not enough to keep you going in a circular path. And obviously your weight has not decreased. So B is the right answer here. All right, 600 degrees. How many revolutions are that? Well, I know that in one revolution I have 360 degrees, and that's equal to 1.7. When the reflection of an object is seen in a plane mirror, the distance from the mirror to the image depends upon which of these? Okay, so here's my mirror, here's my object, here's my image. The distance from the mirror to the image depends only from the object to the mirror. It's going to be exactly the same. It has nothing to do with the observer, as we talked about. It's not the wavelength, and it doesn't matter about the size. Which of these best describe the image of a concave mirror whose object's distance from the mirror is less than the focal point distance? So that means that your object is here. The type of image that it's formed is going to look like this. This is like your shaving mirror. That is a virtual upright magnification greater than 1. So D is the right answer. Consider the rays drawn in this mirror. Which rays is or are drawn incorrectly? Well, let's see. Ray number 1 goes through the center of curvature and then back upon itself. That's okay. So it's not ray number 1, and it can't be rays number 1 and 3 either. This one goes parallel to the axis and then through the focal point. So that one's okay. Which one was that? That's ray number 2. That one checks out. Ray number 3 goes parallel to the axis and through the focal point. What was ray number 2? It went through the focal point parallel to the axis. Hey, let's see here. Parallel. Oh, I through. Yeah, these are all correct. So I'm going to have to rewrite this sentence, and I'll say all are drawn correctly. All right, I'll fix that for your test. That's number 9. All right, let's see, number 10. Is that true? Of course it's true. I think you're all awesome. Okay, so mirror produces an image that is twice the size of the object. So the magnification is equal to 2. The focal length of the mirror is 2 meters. Okay, now I want to ask myself, what kind of mirror produces a magnification that's bigger than 1? Well, it's not a convex because that's always less than 1. So I'm looking at a concave mirror. In fact, that's the answer to one of the questions. And then I want to think about sort of what is the location of the object. Well, in order to get a magnification bigger than 1, I have to have the object inside the focal point, and then that also gives me an upright image. So it's also very important that I think about the sign of this. And I can do that just from knowing that the magnification is bigger than 1, because the only type of mirror that produces an image that has a magnification bigger than 1 is a concave mirror when I'm inside the focal point, and that is a real virtual image. It's like your shaving mirror when you hold it up close to your face. So let's answer these questions. And each of these first 4, these were all worth 2 points each, and this one was worth 7 points. So A, it's a concave mirror. B, is the focal length positive or negative? Well, it's positive because it's a concave mirror. Is the image real or virtual? I've already said that. It's a virtual image. And is the image upright or inverted? It is an upright image. All virtual images are upright, in fact. And then 7, or part E, which was 7 points, where is the image located? Right, now this is a little bit more complicated. I know that my magnification is negative Q over P, and I know that my magnification is equal to 2. So my magnification is negative Q over P. And I also know that this is equal to 2. Now that doesn't help me find Q because I don't know P either. All I know is the focal length, which is positive 2. And I know my magnification, which is also positive 2. Now I also know the mirror equation, 1 over F equals 1 over Q plus 1 over P. I know that this F, I'm just going to replace it here with a 2. So now I have some unknowns. My unknowns include Q and P, and that's all that I know is unknown. That's all that I have, which is unknown. I'm looking for Q, so I'm going to take this equation and solve it for P. And I get P, which is equal to negative Q over M, is going to be negative Q divided by 2. I'm going to take this and I'll plug it in up here. And when I get that, I get 1 over 2 equals 1 over Q plus 1 over negative Q divided by 2. Can rewrite this a little bit. 1 over 2 equals 1 over Q plus negative 2 over Q, or 1 over 2 equals negative 1 over Q. 1 over Q minus 2 over Q is negative 1 over Q. And so Q, however you want to get to this, take the inverse of both sides or cross multiply or whatever, Q is equal to negative 2 meters. So this is my image position. You could, sorry. This is also, as we've drawn it, to the right of the mirror. I didn't expect you to write that or draw an image, just the negative will suffice. But that tells you the negative, that it's on the opposite side from where the object is. All right, let's look at this one. Oh, this was just a cross product. So I know that torque is R cross F. I just wanted you to show me that you can do a cross product. It was only worth 5 points. So R is 4J minus 1K crossed with F, which is 3I minus 2J. Have to get these in the right order, or you're going to get off by a negative, by -1. Now I do FOIL. I do 12J cross I. That's first. Outer is -8J cross J. But if you're astute, you know that that's already 0. Inner is -3K cross I. And outer is, what's that, 2 plus 2K cross J. You have to be careful to get them in the right order, or else they get off by a negative. So J cross I, for example, is equal to negative of I cross J. Okay, now we need to figure out what are the values for each of these, because each of these cross products, J cross I, J cross J, and on, they each have their own vector, and so I need to figure out what that is. This is I, this is J, this is K, and J cross I, first of all, I do my right-hand rule and I get negative K. K cross I, do my right-hand rule and I get positive J. And K cross J, that's equal to negative I. Remember my right-hand rule. For example, here, I let my index finger go in the direction of J, my middle finger go in the direction of I, and then my thumb will point into the page, which is negative K, and you can do the others for the other two. If you want to memorize these, I realized something earlier. This is just a little aside. If you prefer to just memorize these, a good way to memorize them is that I cross J is equal to K. Notice that I have I, J, K, all in a line. Also, K cross I is equal to positive J. Notice I have I, J, and then I come back to K over here. And then finally I have J cross K is equal to I. Notice I have I, J, K in order as I sort of go around in the loop. And then if I switch either one of any of these, J cross I, for example, is equal to negative K. So if you just want to remember these, if you're into memorizing stuff, just remember those three, and then you can figure out the other three. There are only 6 possible combinations, and so if you know those three, the other three are just the opposites of them. Okay, so this gives us in the end negative 2I minus 3J minus 12K. That's in Newton meters. Okay, this is one of the bigger problems on the test. Several parts to this. First of all, what is the net torque that acts on this cylinder? Well, I have a torque 1 up here and a torque 2 up here. I need to figure out, are they clockwise or counterclockwise? Torque 1 is clockwise, so it's negative. Torque 2 is counterclockwise, so it's positive. So the net torque for part A is torque 2 minus torque 1. Torque 2 is going to be 40 newtons times 2 meters, that's the radius of my cylinder, times the sine of 30, minus torque 1, which is going to be 5 newtons times 2 meters. Right, that gives me 80, 40, minus 10, that gives me 30. Newton meters, and actually I have a mistake here, so let me go back and fix it. You've probably already seen it. Torque 2 is right here. That should be positive, and this should be negative. So this is actually torque 1, and this is torque 2. All right, so I actually have negative 30 Newton meters. Sorry for that mistake. But that's the first answer for part A. For part B, I want to know through what angle does it rotate in 3 seconds. I have to take several steps. I have to first find the moment of inertia. Then I have to find the angular acceleration. And then I can find, through kinematics, what angle does it pass through in that time. So first, my moment of inertia, I look back at my table and I look for a cylinder. That's what a disk is, a very flat cylinder. The moment of inertia is 1/2 mr squared. That's 1/2 of 1 kilogram times the radius, which is 2 meters squared, and so that's 2 kilogram meters squared. Next, I find alpha. I know that torque is equal to I alpha. That's Newton's second law. So alpha is equal to the torque over the moment of inertia. I know the torque is negative 30 Newton meters. I is 2, so I have negative 15 radians per second squared. It's negative, so that means it's in the clockwise direction. If I look back up at this, notice, this is the bigger force. It's a lot bigger than this force. Even with the angle, the component of this force in this direction is 20 newtons. That's just, wait, hold on. I need to stop for just a second. Okay, I'm sorry for that interruption. But 40 sine of 30 is equal to 20. So notice I got a bigger force here. That's causing the disk to go in the clockwise direction. We shouldn't be surprised by that. Okay, so now that's my angular acceleration, so it accelerates at that rate. And now really I want to know what is theta. So I say theta is omega naught t plus 1/2 alpha t squared. That is omega naught, which is 0 times t, so that whole term goes away, plus 1/2 of negative 15 times t, which was given in the problem, 3 seconds squared. That's 7.5 times 9. I get negative 67.5 radians. So it travels through that distance, that angle, in that time. So let's see, that is the answer to B. Now in C, what work is done on the cylinder in this time? You can do this in a couple of ways. The easiest way is to say that the work is equal to the torque times the angle theta. Remember, this is sort of akin to what we had in chapter 5 or whatever, where we did work and energy, where the work was force times displacement. The work is our angular force, I'm putting it in quotation marks, our angular force times our angular displacement, torque times theta. So that is our work, and I have these values, so I can just put them in. That torque is 30 Newton meters. I'll put a negative there. Theta is 67.5 radians. I'll put a negative there, and I'm really just putting the negatives in to remind myself that the torque and the displacement are in the same direction. So it's going to give me positive work. And 30 times 67.5 is 2025 joules. All right, so that's one way of doing it, and that's the easiest way, and that's really the way I wanted you to do it. But there is another way to do it that you could also approach it. You could say that the kinetic energy is 1/2 I omega squared. And whatever work that I do on this cylinder will increase its kinetic energy. And so I already know I, that was our 2 kilogram meter squared. Now I need to know what is omega after 3 seconds, and omega is equal to alpha t. Well, that's not that hard to find because I know alpha, it's minus 15 radians per second squared. And t is 3 seconds, so that's equal to minus 45 radians per second. After 3 seconds, it's traveling at that speed. So I'm going to put in my 45 radians per second over here. I leave off the negative because it's squared anyway, it goes away. And then this is also equal to 2025 joules. So either one of those is okay. Now let's look at part D. For D, I want to know, so I take F1 away. So this thing is traveling in the clockwise direction. But then I take away this force, and I only have this force acting. So this force, F2, which is 5 newtons, it's opposing the direction of rotation. So it's going to cause it to slow down as it rotates. And I want to know how long it takes to come to rest. So, easiest way to do this is, well, I need to figure out what is omega at t equal 3 seconds. I've already done that. I did it right here. I'm just going to carry that down. It's equal to minus 45 radians per second. Now look, I'm going to call this omega naught. because now I'm shifting my initial time to when I take that force away. That's my t equals 0. So that's minus 45. Omega final is going to come to a rest eventually, so I'm going to call that 0. I need to know what alpha is. I know that alpha is torque over I, but this isn't the same torque as we had before. This is only the torque that's provided by this force, because that's the only torque that's acting on it, and that's 5 newtons times 2 meters, so it's going to be 10 newton meters divided by I, which is 2 kilogram meters squared, and so that's equal to 5 radians per second squared. So notice my angular velocity is in the negative direction, my angular acceleration is in the positive direction, so it's going to be slowing down. Now I want to know t. I know that omega equals omega naught plus alpha t. T is omega minus omega naught minus or divided by alpha, so that's going to be 0 minus 45 divided by alpha, which is 5. There's my radians. They cancel. One of these seconds cancel, and it leaves me with a time of 45 divided by 5, which is 9 seconds. Let's see, that was probably the most difficult problem on the test. Number 15 largely came from a homework question. I shifted around just a little bit, but it was mostly a homework question, unlike one that we worked in class. Disk has a mass of 10 kilograms and a radius of 2 meters. It's spinning at a certain rate in the counterclockwise direction. So let's just write down the disk, the information that I know about the disk. It has a mass of 10 kilograms and a radius of 2 meters. So I'm going to go ahead and calculate its moment of inertia. It's a cylinder, so that's 1/2 mr squared. 1/2 of 10 times 2 squared, which is 4, so that is 20 kilogram meters squared. I also know that its omega initial is 2 revolutions per second in the counterclockwise direction, so it's plus 2 revolutions per second. You could convert it to radians per second here, but you'll see that that's not really necessary, where with my angular momentum problems, the units just carry through. Then let's look at our bar, or what do I call it, a spinning rod, and the moment of inertia for a rod is 1/12 mb squared. That's 1/12 of 3 times 4 squared. That's 3 times 16 is 48. So this is 4 kilogram meters squared. Let me just write that out. So that's 1/12 of 3 kilograms times 4 meters. That's the length squared, and that's equal to a 12th of 48, which is equal to 4. And then omega naught for this thing is given in the problem, and it is 4 revolutions per second, but in the opposite direction, negative. So now I bring these things together, and I want to know what is their new angular speed, both the direction and the magnitude of that angular speed, or the rotation rate in revolutions per second. Look, this is very much like our perfectly inelastic collisions that we did back in chapter 6 when we were doing collisions, where I have these two bodies that stick together. I have this disk, which is spinning in this direction, and then I have my rod, which is spinning in this direction. They're initially apart from one another, and then I bring them together. And they spin at the same rate. And I want to know which rate that is. So what I know is in this system that I have a certain momentum, that the angular momentum of the disk plus the angular momentum of the rod, that remains constant. And so it's going to equal the angular momentum of the disk and the rod. So the way that's going to look mathematically is I'll say I of the disk, omega of the disk, plus I of the rod, omega of the rod equals the combined moments of inertia. Because they're sticking together, it's like adding the masses up in the perfectly inelastic collisions times their final velocity or speed. And that's what I want to know right there. Okay, so I know all these values. That is 20 kilogram meters squared times 2 revolutions per second plus 4 kilogram meters squared times -4 revolutions per second. This is equal to the combined moments of inertia, that's 20 plus 4 times omega. So I have 40 minus 16 equals 24 omega. Notice that I have more angular momentum going in the counterclockwise direction, so you better believe that my new direction is also going to be counterclockwise because I have more angular momentum in that direction. So I have 40 minus 16, that's 24, equals 24 omega, so omega equals 1 revolution per second. That's part of the problem. And then also in the counterclockwise direction, that's the other part. All right, 16. Stand 4 meters from a convex mirror whose focal length is 2 meters. For a convex mirror, that means my focal length is -2 meters. P is 4 meters. Okay, so I'm looking for Q and I'm looking for M. These are largely just sort of plugging in the right equation. So I have 1 over F equals 1 over P plus 1 over Q. I want to know what is Q. So Q is 1 over F minus 1 over P. Inverse, that's 1 over -2 minus 1 over 4 to the -1. That's -3/4 to the -1. That's -4/3, which is -1.33 meters. Okay, that's Q, and that jives with what I know about convex mirrors, that if my object is over here, my image is over here. That better be when I get the magnification that my magnification is positive because it's upright and less than 1 because it's smaller, and I know that that for a convex mirror is what I should have. So my magnification is -Q over P. That is -1.33 divided by 4, and that's positive, which is good. 0.33 or -1/3 if you keep your fractions there. And so that's the right answer. Magnification, you notice, doesn't have any units. It's just a factor. And I think that's it. There's those multiple choice answers.